So today is the week 12 of our semester, and we will be talking about chapter 12. That's about environmental geology and earth sciences, earth resources. In this chapter, we will be talking about the tectonic plates and how does their movement, that the movement of those tectonic plates, they shape our world. Where and why do the volcanoes and earthquakes occur? And what are some of the environmental and social costs of mining and oil and gas drilling? Also, we will be talking about that how can we reduce our consumption of geologic resources. We will also talk about that why floods and mass wasting are the problems. Let's get started with a case study that's about the mountaintop removal mining. So many mountains in Appalachia are structured like you see the cake layers. They are structured like that with multiple horizontal coal seams that are separated by layers of those sedimentary rocks. The earliest approach for mining this coal was to bore into a coal from its exposed face on the mountainside, either by hand or with mechanical boring machines that has been used most recently. As earth moving equipment has become larger and more powerful, however, mining companies have found it cheaper to simply blast and scrap off the rocks that are lying on the top of those coal deposits. That allows the coal to be scooped by a giant shovel. So this produces far more coal per man hour than the traditional underground mining and brings the high profits to mining companies. Mountain top removal mining, that's the MTR technique, is controversial because of the destruction it weaks on the mountain as well as the water pollution. So this is controversial mountaintop removal mining. It is controversial because like I said, it leads to the water pollution, it destroys the vegetation, and it damages uh, the streams, farms, villages, and also the surrounding valleys. So, as much as 800 feet of rock may be removed from the mountaintop to get to underlying coal. So, sometimes the overburden can be piled back on the top of the mountain or ridge, but often it's seen that it's simply showered into the valley below. So Appalachia won more on more than 500 mountain peaks and ridge lines have been turned into mining wastelands, and about 2,000 miles of headwater streams have been buried of severely polluted, or we can say that is severely polluted by the valley fields that is created by those mountaintop removal mining. So, in theory, the mining companies are required to restore land to its original condition. But when mining is finished, but when a mountain has been flattened and the rock has been dumped into the valley below, it's impossible to create or recreate former conditions. So the denuded mountaintop can be graded, but with no topsoil, or we can so little of the topsoil will grow there. So, in this chapter, we will look at the principles of geology and how they affect our lives. But we will also look at the ways in which we, especially the humans, have become geologic agents. So, MTR mining, that's the mountaintop removal mining, is a prime example of how we are causing long term massive scale damage to the earth. So here in these pictures, you can see that how the mountaintop removal mining is destroying our mountains and especially the rocks. So, Earth processes, they shape our resources. Many people are exposed to geologic hazards of one type or another, but all of us benefit from the Earth's geological resources. So, right now, we are probably wearing several geologic products. For example, plastics of many types are made from petroleum, iron, copper, aluminum mines. They produce electrical wiring that brings you the power. Rare earth metals are essential in your cell phone, your MP3 player, or your computer. So, all of us also share the responsibility for the environmental problems that result from mining, drilling, and processing those materials. As we all know that the earth is a layered sphere, the core, or we can say the interior, is composed of a dense, intensely hot mass of metal, mostly the iron. So, thousands of kilometers in diameter, as you can see in this figure, solid in the center but more fluid in the outer core. This immense mass generates the magnetic field that actually envelops that Earth. So, surrounding the molten outer core is a hot, pliable layer of rock that's called the mantle. The mantle is much less dense than the core because it contains a high concentration of lighter elements such as oxygen, silicon, and magnesium. The outermost layer of the Earth is the cool, lightweight, brittle rock that's called the crust, as you can see in this picture, because it contains a high concentration of lighter elements such as those things. The crust below the ocean is really relatively thin, dense, and young, uh, less than 200 million years old, because of constant recycling. Crust under continents is relatively thick and light and as old as 3.8 billion years with new material that's being added continuously. It also is predominantly granitic, whereas oceanic crust is mainly dense basaltic rock. We all know that Earth is a dynamic planet. There are the primary uses of some major metals that are present are the aluminum, chromium, copper, iron, lead, manganese, nickel, platinum, gold, and silver, and each of them have their own uses. For example, if we talk about the iron is used in heavy machinery for steel production. The manganese, which is a high strength, heat resistant steel alloy. We use nickel in the chemical industry, steel alloys. Aluminum is used for packaging foods and beverages, also in the transportation or electronics. Silver is used for photography, electronic jewelries, etc. And we have some gold that's the medical aerospace that's used that has a medical use, the aerospace, electronic uses, accumulation as monetary standard. Let's now talk about the tectonic processes that reshape the continents and cause those earthquakes. The huge convection currents in the mantle are thought to break the overlying crust into a mosaic of huge blocks that are called as the tectonic plates. These plates they slide slowly across the Earth's surface like wind-driven ice flows on water. So in some places breaking up into smaller pieces and in other places crashing into each other to create new larger landmass. The magma, that's the molten rock, it's forced up through the cracks from new ocean crust that piles up the underwater in mid-ocean ridges. This creates the largest mountain range in the world. These ridges wind around the Earth for about 74,000 kilometers. So earthquakes, if we talk about them, such as the ones that struck Japan in 2011, are caused by jerking as plates, these tectonic plates, they grind past each other. Mountain ranges like those on the west coast of North and South America or the Himalayas that are still rising as the Indian subcontinent collides inexorably with Asia. So Southern California is sailing very slowly with those north towards Alaska. In about 30 million years, Los Angeles will pass the San Francisco if both still exist by then. So these plate tectonic movements, let's talk about them. When an oceanic plate collides with a continental landmass, the continental plate usually rides up over the seafloor, while the oceanic plate is subducted, or we can say it's pushed down to the mantle. That's the layer of the earth, where it melts and rises back to the surface as magma. So deep ocean trenches mark these subduction zones, and volcanoes from where the magma erupts through the vents and fissures in the overlying crust. So those trenches and volcanic mountains, they ring the Pacific Ocean rim from Indonesia to Japan to Alaska and down the west coast of America. So forming the so-called ring of fire where the oceanic plates are being subducted under the continental plates. So a chain of volcanoes like the Hawaiian Islands may form as plates over a hot spot. Where the plates they converge, melting can cause the volcanoes such as the Cascades. Let's now talk about the Pangaea, that's an ancient supercontinent that existed 200 million years ago. It has been found that geologists they suggest that several times in the Earth's history, most or all of the continents have gathered to form those supercontinents. These have ruptured and reformed over hundreds of millions of years. So, over millions of years, the continents can drift long those distances. For example, the Antarctica and Australia once were connected to Africa, for example, so somewhere near the equator and supported those luxuriant forests. The redistribution of continents has profound effects on the Earth's climate, and that may help explain the periodic mass extinction of organisms that marking the division between any major geologic periods. These are the different periods and eras in the geologic time. For example, one era was the Cenozoic, the Mesozoic, and then Paleozoic, and one more is the Precambrian. So the periods were quaternary or tertiary. So these were the first humans or first important mammals. Whereas the Mesozoic eras, when we talk about that, there is extinction of dinosaurs or the first dinosaurs that marks this era marks the extinction of those dinosaurs or the first dinosaurs. And then talking about the Paleozoic eras, that includes the Permian or Pennsylvanian or Mississippian or Devonian. So these mark the life on Earth like first reptiles. So in this era, the first reptiles and fish become abundant, and there were first abundant fossils also. So talking about the Precambrian era, there were the lives that life on Earth was like earlier single celled fossils. The Precambrian accounts for the vast majority of geologic time, that's the origin of the Earth. So now let's talk about some minerals and rocks. What do we mean by a mineral? A mineral is a naturally occurring inorganic solid with a specific chemical composition and a specific internal crystal structure. A mineral is solid, therefore ice is a mineral with a distinct composition and crystal structure, but liquid water is not. Similarly, molten lava, if we talk about, it's not crystalline, although it generally hardens to create distinct minerals. Talking about the metals such as the iron, copper, aluminum, or gold, they come from those mineral ores, but once purified, these metals are no longer crystalline and thus they are not the minerals. A rock, if we talk about, is a solid cohesive aggregate of one or more of those minerals. So within the rock, individual mineral crystals, or we can say the grains, are mixed together and they are held firmly in a solid mass. The grains may be large or small, or we can say these minerals that we are talking about, that the rock is made up of the mineral crystals. They may be large or small depending on how the rock was formed, but each grain retains its own unique mineral qualities. There are three major rock classifications. You might have read about those. That's the igneous rocks, metamorphic rocks, and sedimentary rocks. So rocks are part of a relentless cycle of formation and destruction. These are called the rock cycle. Talking about the igneous rocks, they are solidified from hot molten magma, or we can say lava. So most rock in the Earth's crust is igneous. Magma extruded to the surface from volcanic vents that cools quickly to make those finely crystalline rocks such as the basalt, the rhyolite, or andesite. So these kinds of rocks, they come under the igneous rocks. Now let's talk about the metamorphic rocks. They are formed from the melting, contorting, and recrystallizing of other rocks. So deep in the ground or tectonic forces squeeze, fold, heat, and transform this solid rock. Under these conditions, the chemical reactions that can alter or change both the composition and the structure of the component minerals. So metamorphic rocks are classified by their chemical composition and by the degree of recrystallization. So there are some minerals that form only under extreme pressure and heat. For example, the diamonds, the jade, they are examples of those. And there are others that form under more moderate conditions. For example, the graphite or talc. So some common metamorphic rocks are the marbles that are created from limestone. We have quartzite that's created from the sandstone, and we have slate that's created from the mudstone and shale. Now let's move to the third type of rocks, that's the sedimentary rocks. These are formed when the loose grains of other rocks are consolidated by the time and pressure. The example of sedimentary rocks is the sandstone, which is solidified from the layers of sand, and mudstone that consists of extremely hardened and mud clay. So we have one more tuff that's formed from volcanic ash or conglomerates that are aggregates of sand and gravel. Some sedimentary rocks they develop from the crystals that precipitate out of extremely salty water. Rock salt made of the mineral halide is ground up to produce ordinary table salt. For example, the sodium chloride, the table salt that we usually use in our homes. Salt deposits often form when a body of salt water dries up, leaving a salt crystal behind. Limestone is a rock that's composed of cemented remains of marine organisms. So that was about the different types of rocks, the igneous, metamorphic, and the sedimentary rocks. So this is actually the rock cycle, that how the different types of rocks they are formed. We already talked about them in detail in our previous slide. One more thing about the sedimentary rock experience is the erosion. Particles of rocks that are loosened by the wind, water, ice, and other weathering forces are carried by the wind or water until they come to rest again in a new place. The deposition of these materials is called as the sedimentation, and the erosion can further carve these rocks. We have different colors of soft sedimentary rocks that are deposited in ancient seas during the tertiary period of like 63 to 40 million years ago that have been carved by the erosion. That might be because of the wind, water, ice, or other weathering forces that create that erosion into the fluted spires and hoodoos of the pink cliffs of Bryce Canyon National Park. Let's now talk about the weathering. Most crystalline rocks are extremely hard and durable, but exposure to air, water, changing temperature, and reactive chemical agents that slowly breaks them down. This process we call as weathering. So mechanical weathering is the physical breakup of rocks into smaller particles without a change in their chemical composition. That's called as the mechanical weathering. Chemical weathering, on the other hand, is the selective removal or alteration of specific minerals in rocks. The alteration leads to the weakening and disintegration of rocks, like here you can see in this figure. The weathering has slowly reduced this igneous rock to loose sediment. So exposure to moisture expands the minerals in the rock, and frost may also force the rock apart. Like here you can see those cracks. Let's now talk about the economic geology and mineralogy. What makes the difference? The processes of those plate tectonics and the rock cycle on this planet, they have gradually concentrated uncommon elements and also allowed them to crystallize into new minerals. But this accounts for only about one third of our geologic legacy. The biggest difference is life. So most of our minerals that exist, they are all oxides. But there was little free oxygen in the atmosphere until it was released by the photosynthetic organisms, so thus triggering those evolution of our great variety of minerals. So economic minerals, lead, for example, generally comes from the mineral galena. So lead sulfide and copper comes from sulfide ores such as bornite. That's the copper, iron, and sulfur that's made up of that. So non-metallic geologic resources, they include the graphite, the feldspar, quartz, crystals, diamonds, and other crystals that are valued for their usefulness or beauty. The mining, processing, and distribution of these materials have broad implications for both of our culture and our environment. We all know that metals, they are essential to our economy. They are useful and valuable because they are strong, malleable, and can be reshaped for many purposes. Their availability and use have influenced the economic and political power for individuals and also the nations. Talking about the world industrial consumption of metals, in 2011, the geologists they announced that the discovery of an estimated $1 trillion in metals and other valuable minerals in Afghanistan. So critics claim that this announcement was merely an excuse for continued military occupation of this troubled country. In any case, difficult terrain and political instability will make all these deposits difficult to access. So the rapid growth of green technologies such as the renewable energy and electric vehicles has made a group of rare earth metals especially important. Russia, China, Canada, United States, and Australia, for example, they are especially rich in metal resources. South Africa is unusually rich in diamonds, gold, and other valuable minerals. Currently, the society functions largely on energy that's produced from those geologic deposits of oil, uh, coal, and natural gas. These fuels are created over millions of years as the extreme heat and pressure transform the remains of those ancient organisms. Although there are certain organic rather than mineral, they can be considered part of economic mineralogy and are important geologic resources. Let's now talk about the environmental effects of resource extraction. Extracting and purifying these resources, they can have severe environmental and social consequences. Furthermore, a great deal of water is used in washing the crushed ore with cyanide and other solutions. The USGS, that's the United States Geological Survey, it estimates that in arid Nevada, mining consumes about 230,000 metric cube gallons, or we can say 60 million gallons of water per day after use in ore processing. Much of this water contains the sulfuric acid, arsenic, heavy metals, and other contaminants and is unsuitable for any other use. The Environmental Protection Agency lists more than 100 toxic air pollutants that are released from US mines and wells every year. The most common methods are open pit mining, strip mining, and underground mining. An ancient method of accumulating gold, diamonds, and coal is the placer mining. So, this technique, in which the pure flakes or nuggets are washed from stream sediments. So, since the California gold rush of 1849, placer miners have used water cannons to blast away the hillsides. This method, which chokes the stream ecosystem with sediment, is still used in Alaska, Canada, and many other regions. Another ancient and much more dangerous method is the underground mining. Ancient Romans or Europeans and Chinese miners, they tunnel deep into the tin, lead, copper, coal, and other mining seams. Mine tunnels occasionally collapse and natural gas in coal mines can explode. So water seeping into the mine shafts also dissolves those toxic minerals. Contaminated water can seep into the underground water or groundwater. It's also pumped to the surface where it enters the streams and lakes, making the water, leading to the water pollution. Let's now talk about the methane extraction. A current controversy in the United States involves the extraction of methane gas from coal deposits that are too deep or too dispersed for mining. Because the gas doesn't migrate easily through tight shales, it often takes many closely spaced wells to extract this methane. In Wyoming's Powder River Basin, for example, 140,000 wells have been proposed for the methane extraction. Here you can see the methane extraction well in a shale bed. That's the hundreds of thousands of natural gas wells have been or being drilled in the United States. So often these wells require a controversial procedure that's called the hydraulic fracturing, or we can say the fracking, to release that gas from sedimentary formations. Surface mining destroys the landscapes. The size of modern open pits can be hard to comprehend. The Bingham Canyon mine near the Salt Lake City, Utah is about 800 meters wide at the top. So more than 5 billion tons of copper ore and waste material have been removed from the hole since 1906. A chief environmental challenge of open pit mining is that groundwater accumulates in the pit. So in metal mines, a toxic soup results. No one yet knows how to detoxify these lakes, which endanger the wildlife and nearby watersheds. One more method is the strip mining. So half the coal that's used in the United States comes from the strip mines. So since coal is found in expensive horizontal beds, the entire land surface can be stripped away to cheaply and quickly expose that coal. The overburden or surface material is placed back into the mine, but usually in long ridges that are called the spoil banks. So spoil banks are very susceptible to erosion and chemical weathering. So since the spoil banks have no topsoil, that means the complex organic mixture that supports the vegetation, it has been already removed. So revegetation occurs very slowly. Since 1977, the record of strip mining reclamation has improved substantially. So complete mine restoration is very expensive, of more than uh, 10,000 uh, is needed per hectare. So restoration is also difficult because the developing soil is usually acidic and compacted by the heavy machinery that has been used to reshape the land surface. Here in this figure, you can see this surface coal mine in Saskatchewan was abandoned a century ago. Plants are slowly vegetating the waste rock piles, but the land has little economic or biological value. We all know that one of the most notorious examples of ecological devastation from smelting in the United States is a wasteland near the Ducktown, Tennessee. In the mid 1800s, mining companies they began excavating the rich copper deposits in the area. So to extract that copper from the ore, they built huge open air wood fires using timber from the surrounding forest. So dense clouds of sulfur dioxide that are released from those sulfide ores that poison the vegetation and acidified the soil over a 50 miles area. Rains washed away the soil of the denuded land, creating a barren moonscape. Recently, the upward of about $250,000 per year has been spent on this effort. The trees and other plants are still feeble, but more than two-thirds of the area is considered covered with the vegetation. So when we talk about the smelting, it's the roasting ore to release those metals, which is a major source of air pollution. Chemical extraction is also used to dissolve or mobilize the pulverized ore, but it uses and pollutes a great deal of water. So chemicals used include the toxins like the cyanide. How can we conserve geologic resources? Conservation offers the great potential for extending our supplies of economic minerals and reducing the effects of mining and processing. The advantages of conservation are significant: less waste to dispose of, less land lost to mining, and less consumption of money, energy, and water resources. Recycling also saves the energy as well as the materials. Aluminium, for example, must be extracted from bauxite by electrolysis as expensive energy intensive process. The high value of aluminium scrap gives the consumers plenty of incentives to deliver their cans for collection. So recycling is so rapid and effective that half of all the aluminum cans now on a grocer's shelf will be made into another can within 2 months. One more method that we can use to conserve these resources is that new materials can replace the mined resources. For example, iron and steel have been the backbone of heavy industry, but we are now moving towards other materials. So one of our primary uses for iron and steel has been the machinery and vehicle parts in automobile production. Steel is being replaced by the polymers, which are the long chain organic molecules that are similar to the plastics, aluminum, ceramics, and new high technology alloys. All of these reduce the vehicle weight and cost while increasing the fuel efficiency. Some of the new alloys that have combined with the steel with titanium, vanadium, or other metals were much better than the traditional steel. So ceramic engine parts, they provide heat insulation around the pistons, bearings, and cylinders, keeping the rest of the engine cool and operating all those efficiently. Plastics and glass fiber reinforced polymers are used in body parts and some engine components. The introduction of plastic pipe has also decreased our consumption of copper, lead, and steel pipes. In the same way, the development of fiber optic technology and satellite communication reduces the need for copper telephone wires. What are the different geologic hazards? Earthquakes, volcanoes, floods, and landslides. They are normal Earth processes that have made our Earth what it is today. So, however, when they affect the human population, their consequences can be among the worst and some fear disasters that befall us. Earthquakes are frequent and deadly hazards. So, how these earthquakes happen? When the movement along faults occur gradually and relatively smoothly, it's called the creep or seismic slip, and it may be undetectable to the casual observer. When the friction prevents the rocks from slipping easily, stress builds up until it's finally released with a sudden jerk. The point on a fault which is the first movement that occurs during the earthquake, is called the epicenter. So, one of the most notorious effects of earthquakes is the tsunami. So, these giant swells, sometimes called the tidal waves, such as the one that struck Japan in 2011, can move at 1,000 uh, kilometers per hour or 600 miles per hour or faster away from the center of an earthquake. About 25,000 people were killed and four nuclear reactors were destroyed by the 2011 tsunami. When these swells approach the shore, they can create breakers as high as 65 miles. So these tsunamis also can be caused by underwater volcanic explosions of massive seafloor slumping. So here in this figure, you can see this Japanese earthquake and tsunami in 2011. There was a magnitude 9.0 earthquake, which just off the coast of Japan created a massive tsunami that destroyed homes, killed at least 25,000 people, and also destroyed the four nuclear power plants. So earthquakes frequently occur along the edges of those tectonic plates, but earthquakes sometimes also occur in the center of the continents. The largest earthquake in North America was a magnitude of like 8.8 quake that struck New Madrid, Missouri in 1812. Volcanic ash, it covers damaged houses and dead vegetation after the November 2010 eruption of Mount Merapi in central Java. More than 300,000 residents were displaced and at least 325 were killed by this multi-day uh, eruption. So this disastrous mudslide are also associated with the volcanoes. In 1985, eruption of Nevado del Ruiz, northwest of Bogota, Colombia, caused the mudslides that buried most of the town of Ormero and devastated the town of Chinchina. An estimated 25,000 people were killed. Heavy mudslides also accompanied the eruption of Mount St. Helens in Washington in 1980. So sediments mixed with the melted snow that destroyed the roads, bridges, and property. But because of sufficient advance warning, there are few casualties. Geologists worry that similar mud flows from an eruption of Mount Rainier would threaten much larger populations. Floods are also a part of rivers' land shaping processes. Large rivers often have huge floodplains. Many cities have been built on these flat, fertile plains to be convenient to the river. Floodplains may appear safe for many years, but eventually they flood. So the severity of floods can be described by the height of water above the normal stream banks or how frequently a similar event occurs on average. Talking about the flood control, after the 1927 floods, the U.S. Army Corps of Engineers was ordered to control the Mississippi River. They built the world's longest system of levees and flood walls, but uh, every levee simply transfers the problem downstream. Some now believe that floodplains should only be used for wildlife habitat, parks, and recreation areas. In recent years, however, this elaborate system helped turn large floods into the major disasters. Under current rules, the government is obligated to finance most lease and flood control measures. Many people think that it would be better to spend this money to restore the wetlands, replace the ground cover on the water courses, build the check dams and also the small streams, move the buildings off the floodplains, and undertake other non structural ways of reducing the flood danger. Talking about the landslides, they are the sudden collapses of hillsides. In the United States, landslides and related mass wasting cause about $1 billion in property damage every year. So gravity constantly pulls down on every material everywhere on Earth. So hillsides, beaches, even relatively flat farm fields can lose the material to erosion. Often the water helps to mobilize loose material and catastrophic slumping. The beach erosion and gully development can occur in a storm. So, a general term for downhill slides of earth is the mass wasting. When unconsolidated sediments on a hillside are saturated by a storm or exposed by the logging or road building or house construction, the slopes are especially susceptible to these sudden landslides. Erosion also destroys the fields and undermines buildings. So, construction directly on beaches and barrier islands can cause damage to the whole ecosystem. Normally, the fragile vegetation it holds the shifting sand in place on a barrier lane, but breaching dunes with roads can destabilize those barrier islands, and storms then wash away the beaches or even whole islands. Erosion from Hurricane Katrina in 2005 caused about $100 billion in property damage along the Gulf Coast of United States. This is the aftermath of Hurricane Katrina on the Dauphin Island, Alabama. Since 1970, this barrier island at the mouth of Mobile Bay has been overwashed at least 5 times by the storms. So more than 20 million yards of sand have been dredged or trucked to restore the island. Some beach houses have been rebuilt mostly at public expenses 5 times. So, does it make sense to keep rebuilding in such an exposed place? So, concluding today's chapter, we talked about the geologic hazards, including the earthquakes, volcanic eruptions, tsunamis, floods, and landslides that represent the major threats. So, devastating events have altered the human history many times in the past, sending the geopolitical, economic, genetic, and even artistic repercussions around the planet. The earth resources, including the oil, gas, and coal, are the foundation of our economy. So many materials can be recycled, saving money, energy, and environmental quality. That was all about today's lecture. Thank you.